Oleg's been working on the file system since 2003 as a senior engineer. Right now he works for Whamcloud, and take it away.
Hello everybody. So I'm Oleg Drokin, and today we will talk a little bit about Lustre file striping across large number of OSTs that is also commonly referred as white striping. The things that we are doing with it and the possible future things we are considering and that we would like your input on. So the current situation with the striping is it's actually possible to have thousands of OSTs in the current systems. There are existing file systems with thousands of OSTs, and the OST count in the systems is only bound to grow. There are already systems announced with increased striping than what is available here today. On the other hand, it's only possible to have about 160 stripes per file at the maximum. This is mostly due to a way how we store the striping information. So the striping information is actually stored as an extended attribute in the underlying file system, which is ext3 or ext4 for us. And ext3 only allows us to have a single block of storage for that, which is only 4K for the most common architectures. So the storage itself is pretty sparse as well. So it's like 32 bytes header plus 24 bytes for each stripe description, which includes the OST index number and then the object ID and stuff like this. So 160 times 24 plus 32 gives us about 3872 bytes, which is already close enough to the block size, and plus there's some overhead to store the attribute names, and generally it's a good idea to allow some space for other attributes like extended attributes. So a question might arise, why do we actually need more stripes per file? There are several reasons with various goodness of them. So, of course, first of all, the single file would be limited in bandwidth to about what 160 OSTs can provide. And there are plenty of applications right now that prefer to use a single file to all of their I/O. So where there are tens of thousands or hundreds of thousands threads writing into the same file, the bandwidth is going to be severely limited by those limited number of OSTs. Plus, of course, OSTs don't really like when they're being pounded by thousands of clients. And as the I/O becomes more and more random from their perspective, the performance also additionally drops from the best case of OST bandwidth, where it's just a handful of clients accessing it. The other reason is that the single file size is actually currently limited to around 320 terabytes. This is due to the fact that ext3 file size limit is 2 terabytes. And while ext4 is actually allowing us to have bigger files, there is no way to use that in Lustre currently, because that would be incompatible with existing installations. And there is no way for the OST to communicate this current limit that it supports to the clients or MDSs. And there is currently no way to store this information anywhere in the striping data. So since there is already a demand for the growing stripe count limit, we decided to do some evolutionary growing by just trying to avoid a lot of changes without changing the protocol and to retain compatibility with older clients. The changes that we have made, and I will dive into them later, is first of all, of course, we needed to change ext3 to allow bigger extended attributes. We might have chose a different approach and stored the attributes somehow differently. Say the striping might have been stored as a file body, but we didn't want to do this because that would limit our choices in the future for the case when we would actually want to store the real file data on the MDS, say for small files. Then, of course, to transfer this increased amount of striping information, we need to change buffer allocations elsewhere and accommodate the actual checks in the code that right now assume that stripe size is within a certain limit. Then, of course, the compatibility code needs to be introduced so that we don't actually send those large chunks of data to the older clients that have no idea what to do with it. And also a little bit related to compatibility, the server-side object destroys must be implemented now for certain cases. So we'll start with ext3 changes. Right now, the extended attributes could only be stored as a single block, and there is only a single block pointer from the ext3 inode to store this information. There is no space to store much more stuff like several block pointers or anything like this. So it was decided that an additional inode would be allocated, and we would store the extended attributes as part of body of that inode. That would actually allow us to have huge extended attributes if you really want to, all the way up to the maximum possible file size. Then we will specially encode this inode number and put it into the block pointer in the original inode. This is, of course, is totally incompatible with the older file systems because they have no idea how to read this. So it's one kind of a big change. And you can go back once you start having such extended attributes. This code is originally implemented by Andreas Dilger and later on maintained by Kalpak Shah. The good thing about it is we've got an agreement from ext4 maintainers to adapt this code on the conditions that we actually implement another feature to store intermediate size extended attributes in the total size of up to 64K in a little bit different manner. So we hope to work on that and get this code accepted upstream. Now about the buffer allocations. One of the problems is we actually have no idea how large of a buffer do we need before we actually contact MDS to try to fetch the striping information. So we always must assume the worst possible case of the maximum possible striping, which depends on number of OSTs available. And the more OSTs you have, the bigger allocation is needed. And another problem with the large buffers is Linux actually doesn't like when you try to allocate large amounts of memory by normal means. And large in this context means more than a single page. And if it's over 2 pages, the problems become even worse. So in order to relieve those problems, we decided to switch all such allocations to vmalloc, which is easier for large allocations. It's a little bit slower, as was evidenced recently, but this is actually due to a kernel bug in recent kernels, and hopefully there is work ongoing on fixing this issue. So, of course, all network buffers must grow as well. For our testing purposes, we decided to limit the number of maximum striping at a somewhat arbitrary number of 1352, which is just to contain the buffer growth. Even with that limit, the maximum request size for MDS grows from the current 5 kilobytes to 32 kilobytes, and the reply size grows from the 9 kilobytes to 75 kilobytes, which is quite big. Only if you have a huge number of OSTs in your system, of course. So, of course, older clients still have smaller buffers. And a good and bad thing is we don't actually have a fixed allocation of space in those buffers for the striping information. So we can sort of overshoot the 160 limit we used to have if there is free space because some other parts of the buffers are not used. Still, we need to do certain checks. For the create phase, we actually need to make sure that the client has the small or large buffers, and if it's the small buffers, we need to only stripe all the way up to 160 in a compatible manner. Then all other RPCs that might return striping information, those actually must check that the striping information, whatever that is, would fit into the provided reply buffer. And if it's too small, we will just return EF big error, and so the client just won't be able to work with certainly striped, large striped files. The good thing, as I said, that the buffers are not exactly fixed, so it's possible for older clients to actually work with files striped more than 160 ways. Now, there are some unlink implications. When unlink is performed, the reply actually contains not only the striping information, but also special unlink cookies that are used by the clients to actually destroy the objects and offload this from the MDS. This basically doubles the space requirements in buffers. That's why the reply buffers are actually bigger. And also, there is no reason why older clients shouldn't be able to unlink those hugely striped files. Anyway, any good reasons that I can see. So we decided that, well, we will allow older clients to do that. And since we can't ask them to unlink those objects, the MDS would be doing this now for this case. The obvious downside to that is the MDS-initiated destroy would hog MDS threads and use a little bit more CPU, which is not all that great, but still better than inability to delete your files, I guess. So we have a testing code right now that we tested at Oak Ridge 1300 OSTs file system, and it works reasonably well. There are some problems with it, but they are mostly minor. The older clients also seems to be work, and even all the way with files tracked to around 250, which was somewhat surprising to us, but well. It's just like we expected. The metadata operations for white striped files were a little bit slower, especially concerning the calculation of file size and A time and M time and so on, because mostly we need to contact much more OSTs now to get this information aggregated. The code is actually available for anybody who's interested at git.whamcloud.com. It's in our special Lustre dev repository, and the branch name is white striping. When you check out this repository, don't get spooked by the message that there are no default branches available. That's not an error. This is a warning, so you still can check out the branch after you get this scary-looking message. So what's left in this code is actually to scale back the large buffer allocation and make it dynamic. So we don't actually penalize all file accesses with those large allocations, and instead we would do the default or even smaller than normal allocations. And if we can't actually fit the reply in the buffer, the MDS would return the usual EF big error, and it will actually include the desired amount of space. So the new clients would actually be able to retry the request with a bigger buffer and still work. That way we will only penalize the accesses to the files that are widely striped, and we actually don't expect there to be a lot of such files. Obviously, more testing and stability improvements are needed, and we are working on this, and we really hope that we will be able to merge this into 2.2. So in summary, this is just a brute force evolutionary approach. It's limited in scaling for several reasons. It's not such a great idea to send around megabytes of striping data eventually, I guess. And the attribute scalability is somewhat limited. Like I explained, we need to talk to a lot of OSTs. Hopefully this last problem will be somewhat contained by size on MDS once it becomes ready, and hopefully that will be relatively soon. But now let's talk a little bit about revolutionary approaches. That is, approaches that will change a lot of things in all sorts of incompatible manners that we are considering, and this is where we would actually be very happy to hear your input, and that's very valuable so that we know where to move at. So on top of the list is the so-called single FID scheme. Right now, every file has a single identifier on MDS already that is only used on MDS. The idea is that we will use this identifier on all the OSTs to identify the object numbers and just add the object index to this so that we actually know to which OST we are talking. This alone would just help us to greatly reduce the striping information from the current 24 bytes per stripe to just 2 or 4 bytes just to indicate the index number. If that's not a good enough of a reduction, we can also introduce the index ranges so that we say use 4 bytes to identify the OST index, and then a couple of bytes to indicate how many subsequent OSTs are also part of this striping, which would allow us to specify thousands of OSTs in just 6 bytes of striping information. And in addition to that, Zyrotex came with an interesting idea that we can actually attach a bitmap to that. And that bitmap would indicate that not all OSTs in that range would be used, but only a certain ones which have the bit set. Now, the problem with this approach is basically it brings back the object creates on writes. So the first write will actually create the object that we can't pre-allocate such objects in a reasonable manner. This approach was already tried in some early 1.6 releases, and it brings a lots of troubles with it. So we can't really ensure right now that once the object is destroyed, some out-of-date client comes in and recreates it again. And there are some other problems in this area. So it's not like this is just a very easy approach with this. Certain serious thinking is required before we actually start accepting a code like this or making it. The compatibility of this is, of course, pretty bad, and so existing clients would totally not understand this. If there is a real desire to have existing clients to talk to MDSs that support this sort of scheme, it is possible to have a special unpacking code on the MDS that would unroll this highly condensed format into the traditional existing format. This, of course, would require still the clients to provide huge buffers to contain this message. And it will, of course, again add extra load on MDSs, which are pretty loaded even these days. It's also possible to unpack it on external Lustre proxies that we are planning to implement for quite a while. The problem is the code is still ways off and haven't been seen in the wild. But hopefully, one day, we will have robust proxies and offload this activity and tons of other activities from the stained MDSs. Also, extension of this idea is a non-POSIX separate stream in a single file sim. So essentially each object in a file would represent a separate stream, and there would be no easy way to join those streams together to get a consistent file view. But individual application threads would be able to open just a single file and their own stream in there and write to it just like in a file per process manner. This actually would greatly simplify storage of files and reduce certain metadata overheads so that you don't need to create millions of files anymore and just can do this handful. So I believe this is highly desirable. And of course, it could be the metadata for this could be stored highly efficiently too with the OST index ranges, bitmaps, and stuff like this. Now, everything I have said so far assumes that the clients must know entire layout of the file before they can actually operate on it. If we are to lift this limitation, this opens up some quite interesting possibilities. So we can have, say, complex layouts that are consisting of multiple sub-layouts that are totally independent and just apply to a certain region of the file, like a certain extent of the file. So say, first 5 gigabytes of the file might be striped on certain 5 OSTs, and then next, say, 6 gigabytes might be striped on a completely unrelated 10 OSTs, and so on. It's really like a file join on steroids that really works right. And once we actually have the layout log and have ability to change layouts on the fly, this would allow us to have additional cool features like say you are writing to an OST and you are out of space, you just restripe that particular piece of offset and continue writing to a different OST on a next page boundary. The clients would be able to only request layouts for the range they're interested in the file and only work within that range. This also sort of brings in new problems, like mostly related to file size determination. As it's done currently, maybe the size on MDS would relieve those. There are certain thinking involved. Also, truncate is something that would need to be greatly thought about, because when we truncate a file that's striped in such a way, do we actually truncate just the file, or do we also truncate the layout itself so that it doesn't extend beyond the file size? Those are some thinking involved. But overall, I believe this is also a very interesting scheme that brings up a lot of opportunities. And that's it. Thank you very much. Questions?
Hey, Oleg. So on the brute force method, just making the EA size larger, to avoid allocating the large buffers, maybe you could use a different stripe type to indicate this is this should be a large EA style or large stripe, wide striped file, and then you could just allocate buffers for those type of files.
But that involves much bigger changes to the clients, and the entire idea of this brute force method is that there are existing installations that can't upgrade all of their clients, and so we would want to have those to be able to talk to such files. And besides, it's also somewhat bigger change to the overall client code than we wanted to explore at the time. We really wanted the code to be as simple as possible, so we don't introduce any more layout changes and potentially bugs in that code, which is also very important. And as we know, the current code works pretty well.